Let's talk about error and power and testing, errors in testing and measurement. This is the problem when I look away from the slide as it comes up. Okay, so errors in testing and measurement. Um, where that was weird. So where are we going? Um, First, we're going to talk about error. What is error? Then we're going to talk about a couple different kinds of errors. Some of those are sampling and non-sampling errors. So some that come from uh, when we take a sample from a population, and some that don't come from that. So things that are introduced in other ways. Those include extraneous variables, confounding variables, and bias. Then we're going to look at type 1 and type 2 errors. That's a different kind of error, different use of the word error. Those are errors that can come from those first types of error that we talked about. It'll be fine. It'll become clear when we get to it. And then we'll talk about power. Power. Let's start with error. All right, so what is error? Well, it's the difference between the value obtained and the true value for the population. So kind of like this drawing of Prince. There's the true value and the value that's obtained. Honestly, this drawing is better than I could possibly do, even though it looks nothing like Prince. Um, I would just be like a stick person. Um, and then, like we talked about, within that category of error, between that discrepancy of the actual value of the population and what's obtained, there's two different types, sampling error and non-sampling error. Let's first talk about sampling error. So sampling error is just variation that happens because we're looking at a sample rather than the population. The researcher didn't do anything wrong in this case. It's just that's what's going to happen, right? I mean, this sounds a lot like an Ian Malcolm from Jurassic Park kind of thing, like a life finds a way kind of uh, moment, but error is just going to happen. You're not going to get the exact mean of the population from a sample. It's going to be close, assuming that you've done everything correctly, like randomly sampling and um, pulling, well, a representative sample. But it's just going to happen. It's there. It's expected. Estimates are going to vary from sample to sample. It's fine. In fact, we can account for it. We can quantify the sampling error. Some of the ways that we quantify the sampling error are confidence intervals, standard error, margin of error, and coefficient of variance. Now, confidence intervals, standard error, coefficient of variance, those you're going to see in scientific journals. Um, Not really anywhere else. Margin of error is one that you've probably heard on the news. Anytime there's an election or anything like that, they talk about margin of error. So this is because they're taking a sample uh, from like exit polls or something like that. Of course, they're not looking at everybody. Usually, when they start giving out these numbers, most of the country hasn't even voted at this point. So, of course, there's a margin of error. There's a confidence interval between what they've measured and what the actual end result of the population is expected to be. It's the same thing. Margin of error is in practice. The math is a little different, but in practice, it's about the same thing as a confidence interval, standard error, and coefficient of variance. And really, those just, all those mean are here's a value. Your mean is here. And you expect that the mean of the population is somewhere within this range of that mean that you've obtained from your sample. Let's take a look at that with this little cartoon version. So here's a population. Usually when we're measuring a sample, we don't know the true value of the population. We're trying to infer the population. And actually, if you know what we do in statistics, when you do statistical testing, it's called inferential statistics. The reason it's called inferential statistics is because we're inferring from samples what the population, what the value of the population is. We take samples, hopefully representative samples, and infer the state of the population from those samples. So this is a population here, and we know the mean of it, but this could be like a theoretical population, and we theoretically know what the mean is. But either way, we take a sample. Now, this is like a real sample. If you're doing a study, you'll take an actual sample and you'll find the mean. And you can see that there's discrepancy. Wait, don't I have something that says mean? Oh, no, that was supposed to pop in earlier. Oh well. Those arrows are pointing to the mean. Um, so we have a mean for the sample and we have a mean for the population. The mean for the sample is a little different than the mean for the population, but again, that's just expected. You're not going to, it's very unlikely that you're going to get the exact same mean from a sample that you get for the population, but it will be close. Here's a 95% confidence interval around the mean from the sample. You can see that the mean from the population is within that 95% confidence interval. So we take a measurement from a sample and we say we're 95% sure, 95% confident that the mean of the population is within this range of the mean of the sample that we've grabbed. All right. So error is going to vary based on sample size. Um, Say that we want to gauge the attitudes of an entire town um, in an unknown state, but the city we know is Springfield. Um, we can take a look at just a family of five. We can gauge their attitudes on something, and that's going to end up with a large amount of error because we just have five people, and we're trying to generalize to a town of, let's say, 100,000. It's difficult to know if our five people, how representative they are. So we're going to have a large confidence interval, a large margin of error. But if we sample 50 people or 100 people, we get a much closer look at what the town's average actually is. So to put it another way, sample size is inversely proportional to the size of the error. A larger sample size is going to correspond to a smaller error. And a smaller sample size is going to correspond to a larger error. So the more subjects that you can actually grab to test, the more confident you are that your mean is within a certain distance of your sample mean. Your population mean is within a certain distance of your sample mean, right? So key thing to take away here, larger sample size, smaller error, because you're measuring more people. This is another way to look at it. This is just kind of a graph of like you take a measurement of one. It doesn't really look like what you would expect your normal distribution to look like. As you measure more and more people, you get closer to this shape of a natural distribution, normal distribution that you're expecting. And this is another version of this. This is from a study. Here's the thing about this study. This study is old. It's only it's only 10 years old. It's published in 2013, but the concept just seems so old. And the concept is proportion of smartphone owners in the UK by sex. The fact that neither of these is anywhere close to 100%, that's why I say it seems old. There are studies that are from the 70s that don't even seem this old. I mean, of course, there's a lot more time in between now and those studies, but just the fact that only 50% of males in the UK had a smartphone, it's weird, man. I think it's important to note that it's not cell phone. People still had those like little flip, phones, and they do the T9 texting and they'd get a cramp in their thumb, and then, you know, this is smartphones only, iPhone, Android, etc. What you can see is on the left, this is 50 men and 50 women. Look how large those confidence intervals are. They're huge. In fact, when these bars overlap, you wonder, is there a statistical difference between those two values? It looks like maybe there's not. But In the right two columns, you see that now we're looking at 500 subjects, 500 men, 500 women. The error has shrank considerably. In fact, now it looks like there might actually be a statistical difference between cell phone ownership for men and women in the UK. Roughly 50% of men and 68% of women, something like that. So women are more likely to have smartphones than men in the UK in 2013. I'd be willing to bet that if we did this study now, it'd be about 90%, 95% of respondents have smartphones. And the other percent that don't want to have a phone. There's probably very few people that are just like content with their BlackBerry. Okay, let's keep going. Let's talk about non-sampling error. All right, non-sampling error. Let's jump back a second. Remember, sampling error is natural variation. It's normal. In a way, it's kind of cool. There's like a beauty to the fact that the numbers vary, but we can still infer something about the population. It's it's interesting. Yeah. Non-sampling error. This is bad. This is really bad stuff because when we have non-sampling error, what is it? It's a term for errors that are a result of factors other than taking a sample. Those factors are going to result in bias, a biased sample. That's not good. That's random variation is great. It's cool. We can quantify it. Non-sampling error is hard to quantify because we're not necessarily sure what's going on, and it can lead to actual wrong conclusions. So let's talk about bias. Bias is error in the design or execution of a study which produces inaccurate results. Something is wrong with the system. You've measured the wrong thing, or you have chosen the wrong sample. It creates an association that isn't true, an association between two variables that just isn't true because of some problem in how the study was designed or how the participant pool was managed or how the responses came out, some actual legitimate problem that isn't just random variation. Some common types of bias are a non-representative sample. We talked about sampling in earlier lectures, but essentially we want to take a representative sample, whether that's random sampling, whether it's stratified random sampling, or any of the other methods of sampling. We want to stick to the one that we've chosen. Non-representative sample, that could be a convenience sample. You hope that your convenience sample is representative, but there's really no reason why it would be. So that's a non-representative sample. Non-response could be that you have chosen randomly, correctly, a random group of people, but within that group of people that you've surveyed, there's a systematic way in which some of those participants don't answer questions. And so what you get is you only have answers from a certain subset of those random people that you've chosen. And that introduces non-randomness again. Also voluntary. So if you have a survey that you put out to everybody and you can just volunteer to take it, there may be a systematic bias for people that are going to take that survey. So again, you've entered something non-random into your data pool. You can also have response bias, and these are like leading questions. So a question beforehand that leads you to answer a certain way on a subsequent question. Imagine the question is, do you need to use the bathroom right now? And people would say, I'm all right. And then a leading question might be, think about a waterfall and a fire hose. And listen to this sound of a babbling brook. Now do you need to use the bathroom? And more people might say yes. That's like a leading question. Another one is social desirability, which is sometimes called faking good. It's called faking good. But you could also call it faking bad and spend like 30 minutes making a graphic for a slide that's going to be on screen for about 5 minutes. Um, but I hope you enjoyed it. Uh, so social desirability, you're just going to answer a way that you think society would appreciate. Um, when I was in high school, we had to answer these questionnaires for DARE, and what tended to happen was kids that actually probably were using illegal substances would be like, "No way, I never drink alcohol. I'm 13." And they did. And then other kids like me would be like, "Yeah, I'm totally edgy. I smoke every day." And you know, we're that did not happen. We're just like trying to seem cool, even though these are like presumably uh, anonymous surveys. Kids are weird, but so are adults. And social desirability answers come up even when you expressly tell people like these are anonymous surveys. Names aren't known. We have no way to trace it back to who answered this. Sometimes you still end up with social desirability um, answers, faking bad. The measurement tool or measurement error could be a bad tool, an unreliable tool, an invalid measurement. Recall error is that participants just can't accurately remember all the information. You ask somebody how their day was, rate it 1 to 10. It's possible that there's something really good or really bad that stood out, but if they went back and accurately cataloged their day, their answer might be a little different. Or you ask them, um, how many times a day do you uh, how many times a day do you snack on something? People think they snack a lot less than they actually do. I'm very guilty of that because Doritos are delicious. Publication bias. They've got a whole slide on this. Which comes next? Okay. Um, so a way that we can control for let's just okay. Let me go forward. We're going to talk about publication bias, and then I'll go back. Publication bias is a bias where journals like to publish um, statistically significant results. It's a problem. Like it makes sense. Statistically significant results are more like, oh, interesting. This has a relationship here, and non-significant results are sometimes like, you know, kind of a downer. Oh, that experiment didn't turn out, but that doesn't mean that the information isn't useful to know that some study that someone didn't work out. How many times, because we don't publish these studies, has the same research been done across the world? And if we published non-significant results, people would stop wasting time doing that research. But I could go on about the academic publication system for a while. Anyway, the fact of the matter is that statistically significant results are 3 times more likely to be published than insignificant results. Um, Also, researchers, because of this, just don't submit non-significant results too. So it's not that all of your significant results and all of your insignificant results are submitted. Researchers know that you don't submit non-significant results. So there's a lot of non-significant results that are probably never submitted at all. Um, Also, journals are more likely to publish catchy results, and non-significant results are never catchy. So you put them in a file drawer. This is typically called the file drawer problem, and um, you can also feed your null results to sharks. Okay, let's go back to how do we control for bias? Well, there's a couple ways we can do this. In the design phase of our research, we can strictly define what it is we're looking at. This is also called operationalization. So if you operationalize your variables, you have a very strict, precise definition of what it is you're measuring. What counts as snacking? Can it be one piece of candy, or does it have to be like a systematic, like you're sitting down and eating multiple things throughout the day? If you find a chip in your pocket, does that count as snacking? Um, that's a whole other thing of like, you know, people that find chips in their pockets, I guess. But this would be the strict definitions. Really define what it is you're looking at so that there's no slop. Um, People could replicate the study and get the same result if you strictly define what it is you're looking at. Different raters are going to rate the same way because there's a strict definition. Randomization, of course, you want to grab participants and you want to randomly assign them to different conditions. That way, there's no systematic bias introduced for who gets assigned to different conditions. So, no, if you're testing out a pain medication, no medication, traditional aspirin, and a new pain medication. You want to randomly assign people to those three groups and not the first people that came to the study get this one. The second group of people that came to the study get aspirin. The third group of people that came to the study get the new one. There could be something about being early or late to the study that changes the results. So randomizing uh, assignment to groups is a important component of controlling for bias. You want to match controls. So you want to match participants if possible. This is another way that you can do this. So you can have a participant is like a 30-year-old white male, um, speaks English as a first language, lives in Arizona. You want to also, in your other group, have a 30-year-old white male who speaks English as a first language and lives in Arizona. So those are like matched controls. Of course, they're not the same person, but they're like closer to being the same person than, say, a very old woman who lives in North Dakota. There's not as much of a reason why those people, especially if you're doing like a study on running, like a 90-year-old, 95-year-old woman in North Dakota in the winter is probably not running as much as a 30-year-old man in Arizona in the winter for so many reasons. So matching is another way to control for bias. Blind studies. You've probably heard of double-blind control studies for drug research. This means that the people that are being tested don't know if they're getting a placebo or an actual drug, and the doctors that are assessing them also don't know. Sometimes, even though the doctors don't say anything, like, oh, hey, how's that placebo treating you? Of course, they're not going to do that, but even if they did know, they might treat the participants differently, which leads to a different outcome. So, blind procedures of keeping the subjects in the dark and the doctors who are testing them in the dark leads to more accurate results. It's another way to control for bias. And also, in the analysis phase, we can standardize our results. We talked about that just one lesson ago, right? So taking z-scores, standardizing the results together so we can accurately compare scores on different measures. Oh, we went over that slide. Let's talk about confounding. So what is a variable? We've talked about this, but a variable is an object, event, idea, a feeling, a time period, or whatever that you're trying to measure. It could be a new surgical procedure. Compare a new surgical procedure to the old surgical procedure. So invasive surgery versus some sort of laparoscopic procedure. Political party affiliation. A new drug, a different milligram prescriptions of that drug. So 0, 10, 20, 30 milligrams. Um, what food you eat. That's a delicious assortment right there. I'm kind of hungry right now, if you can't tell. And then, or language. What language you speak. Or if you speak one or multiple languages. These are all possible variables that could exist. Okay, so some types of variables. Again, we covered this, so this is kind of a review. I'm going to blow through this one a little quickly, but an independent variable, this is the one that's by itself. It's not changed by other variables that you're measuring. Independent variable is like you're assigning people to different conditions. So 0 milligrams, 10 milligrams, 20 milligrams, that's independent. You've assigned people to this. It is the political party affiliation that they come in with. So it's not going to end up changing. Your dependent variable then is how much pain do you perceive? It depends on the amount of pain medication you got 0 milligrams, 10, 20, 30. And what you're doing is you're measuring the perceived pain from your participants depending on which of those conditions they're in. Um, Response to a type of political ad. And that might change based on the political party affiliation that participants come in with. An extraneous variable. Here we go. These are some new concepts. These are not the variables of interest, but they influence the outcome of an experiment. Consider like the temperature in the room where you administer a test. So if you have some foods and you say like, hey, which food is um, most appealing right now? If the room's really cold and you have a hot pocket and a ice cream, people might go for the hot pocket because they're already freezing. They don't want to be more cold. And if it's a warm room, they might go for the ice cream. Um, so the temperature in the room, these are extraneous variables that could influence what's going on. You also have confounding variables. A confounding variable is one that's associated with both the exposure and the outcome and can make a relationship look different than it actually is. So it's like you see an association that could be true. There's something going on between two variables, but what's actually going on is this third variable is pushing both of them. It's a misleading association between the first two. Let's look at, we talked about those. Let's look at these examples. So here's a confounding variable. We've got the exposure and the outcome. We're measuring those two. The large arrow is saying like, oh, we think there's a link between these two. Really what's going on though is this confounder is changing both of them. A couple actual examples of this are alcohol consumption and heart disease. Now, if you do a study where you take a whole bunch of people and you measure only alcohol consumption and heart disease, it looks like people who drink more have more occurrences or are greater risk of heart disease. But when you also ask about smoking, what you find out is that smoking is correlated with alcohol consumption and smoking is correlated with heart disease. So once you get rid of that association there, the correlation between alcohol consumption and heart disease goes away. This is also true and even more glaring, I think, with smoking and coffee consumption. There's a lot of studies that have been come out in the last, I'd say, 5 years that show that coffee consumption tends to be beneficial for some health problems, not all of them, especially not if you have heart problems. Um, Consult with your doctor. But there are some things that show that coffee consumption can have protective effects occasionally. But if you measure coffee consumption and pancreatic cancer rates, it looks like drinking coffee is associated with higher rates of pancreatic cancer. But again, freaking smoking, if you also measure rates of smoking, it just occurs that people who smoke tend to drink more coffee, and people who smoke tend to have more pancreatic cancer. When you look at among just smokers, then all of a sudden the correlation between coffee consumption and pancreatic cancer goes away. If you look at just non smokers, the correlation between coffee and pancreatic cancer goes away. So, really, it's pushed by the smoking. So sad that coffee gets a bad rap sometimes. Okay. In the design phase, some ways that we can control for these, conceptually think through the issues. What else might be contributing to these two variables? Is there anything else I should measure because it might be affecting both variables, temperature in the room? Randomization, again, we talked about that. Matched controls, talked about that too. In the analysis phase, don't measure two variables, or actually, sorry, don't analyze two variables that measure the same thing. So socioeconomic status and income are measuring the same thing. If you do that, This is kind of a high level concept, but there's variance associated with each one as you start. They're highly correlated, so they share some of the same variance. But if you analyze one and then you go to analyze the other, you're kind of analyzing the same variance pool twice. Definitely include potential confounders in the model. So smoking. Include smoking in your model. What you've learned here is always ask if someone is a smoker. Not really, but it's kind of like that. If you're measuring something like coffee consumption and cancer, include smoking, include other things that we know are associated with higher rates of cancer so that you can test those and pull that out of your model to see if these other two variables are still related. Okay, so now, big change right here. We're going to move to type 1 and type 2 errors. It's a slightly different way of using the word error. Okay, you'll see what I mean. We can also have errors in decision making. So it's possible that when we make a decision about our statistical test, it's incorrect. Now, again, this doesn't necessarily mean that anything was done wrong. This could come from sampling error, it could come from non-sampling error and bias, but they're possibilities. So when you do a hypothesis test, there's 4 possible outcomes. One is you fail to reject the null, but the null was true. You fail to reject the null, and the null is true. Whoop! I said that wrong. You fail to reject, and the null is true. Okay, great. And then also you could reject the null, and the null is false. That's great. Both of those are correct decisions. The null is true, keep it. The null is false, reject it. Cool. These are great. This is what we're looking for. But we could also reject the null, but it was true, or we could fail to reject the null and it was false. Those are type 1 and type 2 errors. And that's all I'm going to say about those. Good luck on your exam. No, I'm kidding. Let's talk a little bit more about type 1 and type 2 errors. So here's a table showing you that you fail to reject and the null is true. It's correct. Null is false. Reject the null. Correct decision. Null is true. Reject the null. Type 1. Null is false. Fail to reject. Type 2. How do I remember these? Because if you could just if you have a photographic memory, take a picture of this table, put it in your brain, you're good. But if you're normal and you have flawed memories like the rest of us, think of it like this. There's 2 ways that I think of this. Type 1 error is like type A. Type 1, type 2 error is like type A and type B personalities, right? You've got both of these. Type A personality is like like that. And a type B personality is kind of like, it's cool, everything's fine, right? A type A personality is way more likely to make a false alarm because they're like awake and they're doing all these cool things and they're like, oh, there's a UFO. Oh, no, sorry. That was a bird. And that's like a false alarm, right? So type A, type 1, false alarm. And if you look at it, the null is true, which means nothing is happening, but you've rejected the null. It's a type 1 error. It's a false alarm. You rejected the null, you said something was happening, but really it wasn't. False alarm. And then type 2, which is like type B, very chill and calm, and they fall asleep a lot. I'm a type B personality, so I can attest to accidentally falling asleep sometimes. And so what happens here is in reality, the null is false. Something's going on, but you failed to reject the null. You said, no, it's fine because you were sleepy. And you're like, there's nothing going on. It's fine. But there was. So that's a type 2 error. So type 1, type A. Type 2, type B. False alarm. Or, oh, I didn't catch it. I was asleep. Hopefully that helps you out. Okay. Here's another look at type 1 and type. Whoa. Here's another look at type 1 and type 2 errors. So type 1, if the null hypothesis is rejected when it's actually true, like this doctor telling this guy He's pregnant. This old man. Congratulations. Um, there's so many reasons why that it's it's not. There's so many reasons. Type 2 error is this woman proudly clutching her baby, and the doctor says, "Hey, you're not pregnant," because the type 2 error is the null hypothesis is actually false, which means the null hypothesis in this case is that someone is not pregnant. She obviously is. We would reject the null. We should be rejecting the null, but the doctor is making the error to accept the null hypothesis. You're not pregnant. So type 1 and type 2 errors. Okay. If you want to relate this to p-value, so type 1 error, the p-level is a little too tight. Type 2 error, p-level is a little too loose. Okay. Let's talk about type 1 errors in another way. So it's the probability of rejecting type 1 error is not the probability of rejecting the null hypothesis. It's related to type 1 error. We talk about this as alpha. So the probability of rejecting a null hypothesis when it's true, which would be a type 1 error, is alpha. Alpha can range from 0 to 1. Our usual levels for alpha are set to either 0.01 and 0.05. This is when we decide if something is less than this, we say that this is statistically significant. Our typical rule of thumb of 0.05 was pulled right out of thin air. And if you've played Super Mario Brothers 2, is it Super Mario Brothers? When it was on the NES? Mario Brothers 2. The sound of this dinosaur shooting an egg out of its mouth is kind of probably what it sounded like when somebody decided that we were going to set our alpha level to 0.05, just as a discipline. Like that. Um, it's arbitrary. Some people go to 0.01, which is a little more conservative. It's harder to obtain a value that's lower than 0.01. So it's more difficult to get a statistically significant result, which protects you against making a type 1 error. The alpha level is usually set, it's always set by the researcher, but usually we just go with convention of 0.05. All right, type 2 error. Probability of failing to reject a null hypothesis when it's false is represented by the Greek letter beta. So type 1, this here again, this is your type A personality, type B personality, right? Alpha, type 1, type A, alpha, type 2, type B, beta. So beta is the probability of failing to reject the null hypothesis when it's false. It also can range from 0 to 1. Alpha and beta are related to each other. So as one goes up, the other goes down. Higher alpha, lower beta. Higher beta, lower alpha. To calculate beta, you need to have a little prior information about the mean and standard error of the population as well as the current sample size. So we're going to take a look at this in a couple slides. So let's think about this. Which type of error does our criminal justice system favor? Which is the idealized version of our criminal justice system. So innocent until proven guilty. There's all sorts of, horrible court cases where we can show that that wasn't true, but innocent until proven guilty. So we're way more likely, we should be way more likely to let a guilty person go free than to convict someone who isn't guilty. So, which is that? While I jump back, think about it. All right, here we go. So, we have our false alarm, or, oh, I guess I fell asleep. Well, false alarm means we're putting a lot of people in jail who shouldn't be. So our criminal justice system should be functioning on the, oh, I guess I fell asleep model, which is a type 2 error. So let's take a look at that. Type 2 error is the null is false which means that the person is guilty. The assumption is the null hypothesis is innocent. So the null is false, which means guilty. And then you failed to reject, which means the guilty person has gone free. Null is innocent. Null is false, which means the person is guilty. You failed to reject the null hypothesis, which means you maintained over here innocent. So you let an innocent you you let a guilty person go free because you're protecting the innocent people from going to jail. It's a type 2 error. Okay, let's go back. This is your table again. Keep an eye on it. And now let's talk about power. Power of a hypothesis test is the probability of rejecting the null hypothesis if the null is false. We're looking at this green one right here. This is 1 minus beta, so it's exactly the opposite of the beta that we just calculated. So in other words, the power is the ability of the study to find a difference if it actually exists. So this little graph right here is going to show you how all of these things interact. This is alpha. In this case, it's alpha divided by 2. That's because it's a two-tailed test. But you can just think of it conceptually as here's alpha. And then we've got, that's this distribution over here. And then within this one distribution, so you've got a whole, one whole, piece of one whole pie. You've got beta as the red portion of that pie and power, which is 1 minus beta, as the other portion of that pie. They're exact opposites of one another. Power is exactly the opposite of beta. They should add up to 1. They should add up to 1. They're like one whole pie. Just one is a slice and one is the rest of the pie with the slice taken out. Power can be affected by 4 things. The effect size, which is how big of an effect there actually is, how far apart the distributions are. Whoops. The sample size, how many people or items you're actually testing. Remember, a larger sample size is going to be a smaller error. The level of significance that you choose, so 0.05 versus 0.01, and the power. So all of these are pulled from, like, these all have mathematical ways that we can derive all of these different things: effect size, sample size, significance level, all of these. What that means is you can put it into a formula so that if you know 3 of them, you can figure out the other one. You can also estimate your parameters. So you can use the same formula that you're throwing all these into to get the missing one. You can estimate your parameters based on previous studies that you've done or that are in the literature to kind of figure out what sample size you would need before you actually do your research. So this is necessary because you don't want to need 100 participants and you get 50. Then you've wasted a lot of time getting participants, and it's unlikely you're going to be able to detect an effect if it's actually there because you don't have enough participants. If you do this power analysis ahead of time, then you would know how many participants you should grab. To sum up, error is the difference between the value obtained and the true value. Bias is an association that is not true between 2 variables. Sampling error, remember, random variation, it's fine. Non-sampling error creates bias, it's not fine. An extraneous variable is something that influences the outcome of an experiment, and a confounding variable describes an association that is potentially true, it looks like it's true, but it's actually misleading. Type 1 occurs if the null hypothesis is rejected, but it's true. Type 2 Occurs if the null hypothesis is not rejected, but it's false. Remember also, not on this page. Type 1, false alarm. Type 2, I saw nothing. Let's talk a little bit more about power. Power is the ability of the study to find a difference if it actually exists. You can calculate this in the study design phase so that you know how many participants you need to measure. And this is the kind of thing that you would see if you're pre-planning how many participants you need. So on the basis of previous studies, we estimate that 20% of patients would achieve the primary outcome with intensive medical therapy, 83% with gastric bypass, and 50% with sleeve gastrectomy. We determined that 150 patients, or 50 per group, because we just talked about 3 groups, would provide a power of 80% to detect a difference between the 2 surgical groups, a power of more than 99% to detect any differences among the 3 groups. So they've done this power analysis by looking at previous research. So they know that 20% of patients get the outcome they're looking for, 80 with medical therapy, 83 with gastric bypass, and 50% with sleeve gastrectomy. Then they put those percentages into a formula to calculate how many participants they actually need, which comes out to be 50 per group, or 150 total. Okay, if there's anything that you are still not sure about, something that's just not quite sticking in there, check out these videos for a little bit more of in-depth look into what we've talked about, and also this page. You have access to these slides, so you should be able to click on those if you're confused. And remember, type 1, type A, false alarm. Type 2, type B, I sleep. Okay.